Hello everyone, in this video we shall be deriving some important expressions of electric field with the help of Gauss's law in electrostatics. So Gauss's law in electrostatics states that the net flux emanating from a closed surface consisting of charges is given by phi E, which is your net electric flux, is Q net by epsilon naught. Here Q net is the net charge enclosed by the Gaussian surface. So suppose this Gaussian surface has Q1 and Q2 charges inside it and the charge Q3 is outside the surface, then your Q net will only be Q1 plus Q2. We are not going to consider Q3 as it resides outside the surface. Now, through a small elementary area, the net flux which emanates is given by d phi E is equal to dot product of electric field vector and the area vector. Now for a surface, the area vector is always along the perpendicular drawn to it. So this is your ds vector. The area vector is always perpendicular to the plane of the surface. So the total flux will simply be integral of d phi E, and that is integral of E dot ds, and we also know that phi E is equal to Q net by epsilon naught. So this equation we are going to use to derive the expressions of various electric field vectors. Now first we shall be deriving the electric field due to an infinitely long charged wire. So here we are going to consider a straight infinitely long positively charged wire having a charge density of lambda. Here lambda stands for the charge per unit length. So this basically is your infinitely long current carrying wire having positive charges and the charge per unit length being lambda. Suppose if we intend to measure the magnitude of electric field at the point P, what we must do is we must draw a Gaussian surface such that the point P lies on the circumference of the Gaussian surface. So here the Gaussian surface will be in the form of a cylinder. Here the cylinder has three surfaces. Number 1 is the top circular part, number 2 is the curved part of the cylinder, and number 3 is the bottom circular part. So the area vectors for all these three surfaces will be as follow. For the surface 1, that is the top circular part, the area vector will be in this direction because it's a perpendicular drawn to the surface. For the curved part, the area vector will be in this direction, and for the bottom part the area vector will be in this direction. Now the integral form of Gauss's law says that the integral of dot product of E and ds is equal to Q net by epsilon naught, where your Q net is the net charge enclosed by the Gaussian surface, and we are going to assume that the height of the Gaussian surface is L. So if the height of the Gaussian surface is L, the net charge will be lambda, which is your charge per unit length, times L. Now the integral E dot ds is equal to q net by epsilon naught. This integral I can divide it for three parts for each of the three surfaces. That means for surface 1, which is your top circular part, for surface 2, which is your curved part, and for surface 3, which is the bottom circular part, and your q net being lambda L by epsilon naught. Now we know that dot product between two vectors is given as the product of their magnitudes and the cosine of the angle between them, plus ds cos theta for surface 2 plus eds cos theta for surface 3 is equal to lambda L by epsilon naught. Now what is the direction of the electric field vector? As we know that the wire is positively charged, so the direction of the electric field will be away from the wire. So this is the direction of the electric field. Now as you can see, for surface 1, that is the top circular part, the angle between ds and electric field is 90 degree. So here we are going to put theta as 90 degree. So number 1 is eds cos 90, and for the surface 2, from the figure you can see that both E and ds are in the same direction. That means the angle between them will be 0 degree. And for surface 3 as well, the electric field vector and the area vector are perpendicular. That is, theta is 90 degree. We know that cos 90 is 0 and cos 0 is 1. So substituting these values, we are going to get EDS for the second surface is equal to lambda L by epsilon naught. Now since E is not a function of the area vector, it will come out of the integral. That is, sorry, this should be lambda L by epsilon naught, and the integral of ds will be s, and since this integral is done over the second surface, that is the curved surface, s will represent the area of the curved surface, that is s2. Now we know that the curved surface of a cylinder is given by 2 pi r L, where r is the radius of the Gaussian surface. Basically, r is the distance of the point from the system of charge. So E into 2 pi rl is equal to lambda L by epsilon naught. So from here we can cancel out L. So E becomes lambda by 2 pi r epsilon naught. This is the expression of electric field due to an infinitely long charged wire. And from here we can see that E is dependent on the radial distance